Here are the solutions to problems 23, 24, and 25 from your energy review. 23, a wrecking ball swings at the end of a 12-meter cable, and it's on a vertical circular arc. The crane operator manages to give the ball a speed of 5 meters per second as the ball passes through the lowest point of its swing, and then gives the ball no further assistance. What speed does the ball have when the cable makes an angle of 20 degrees with respect to the vertical? Okay, first things first, we need to figure out all of our information here. So we know the cable is 12 meters here. We know it's 12 meters, long there. The question is, how much higher does this cable go, or does the ball go, I should say, because it's going to swing from a low point to an angle of 20 degrees. Well, if the total length here along this side is 12, and you see how we sort of made a little right triangle out of the straight up and down and the 12-meter length hypotenuse. If we can figure out what this adjacent side is, it's going to be some portion of 12, something less than 12. And once we know what that is, the difference between this guy, the adjacent side of this triangle, and the total length is going to be the height difference, as you can see in the picture. So how do we do that? We're just solving for the adjacent side of this right triangle, and to do the adjacent, when we have the hypotenuse, we're going to use the cosine. So cosine of 20 degrees is the adjacent over the hypotenuse, which is 12 meters. I'm going to multiply the hypotenuse over to the left side, giving me cosine of 20 degrees times 12 meters will be 11.28 meters is the adjacent side of this triangle. Well, if 11.28 meters is from where the cable originates down to where it will be when it's swung at an angle, that leftover distance is the difference between those, which is 0.72 meters. So that's how high the ball goes at that point in time. That's what makes this a challenge problem, is that you had to do that part first. From here, it's actually pretty easy. Initially, I'm going to call when this thing is at its lowest point, and then the final point is going to be when it's at 20 degrees. Initially, does it have potential energy? I'm going to say no, because yes, it's on a cable, but that's not a bungee cord, so there's no elastic potential, and it's at the lowest point we care about, so no gravitational energy. It is moving at 5 meters per second, so it is going to have kinetic energy. When it gets 20 degrees into the swing, it's going to have potential energy because it's higher. That's what we just solved for, the H, and it's going to have some kinetic energy because we didn't say that was the highest point in the swing. We just asked how fast is it going when it gets to that point. So it's going to be something other than zero. It's going to have kinetic energy. Rewriting my equation without that initial potential in it gives me KE1 equals PE2 plus KE2. Now I'm going to expand each of those. Kinetic energy is 1/2 mv squared. Potential energy is mgh. And kinetic energy over on this side is 1/2 also mv squared. That's just the final velocity. There's an m in every term, and they cancel out. From here, with writing it without the m's, I get 1/2 initial speed squared equals gh plus 1/2 final speed squared. I'm solving for the final speed, so I'm going to subtract gh over to the left side, which is what we have down here in this line of the equation. 1/2 initial speed squared minus gh equals 1/2 v final squared. And I multiply by 2 to get rid of the half, which is where there's a 2 in the gh, and the 1/2 disappeared with the initial speed, and do the square root to get rid of the squared. Plugging in all my numbers, I get the square root of 5 squared minus 2 times 9.8 times 0.72. Once I put that in my calculator, I get that the wrecking ball will be moving 3.3 meters per second when it's at 20-degree angle with the vertical. Moving on to 24. A 6-kilogram box of oranges is placed on a frictionless ramp and begins to slide down. When it reaches the bottom of the ramp, it continues to slide on a flat surface until the friction on the flat surface causes the box to stop. What is the force of friction acting on the box when it is sliding along the flat surface? There's no picture drawn for this one because it's already on the review paper. So you have to take a look at it and say, when are we first looking at this thing? We're first looking at it when it's on the top of the hill. When are we done looking at it? When it's come to a stop. Well, at the top of the hill, it's got a lot of potential energy because it's at the top of a hill. It's starting from rest, so it's got no kinetic energy. At the end of the problem, it's not going to have any more potential energy because it's on the flat, lowest possible surface. It's not going to have any kinetic energy because it's stopped. So all of the energy has been taken away by frictions or thermal energy. So when I rewrite this equation without all the x'd out stuff, I get my potential energy, mgh, equaling my thermal energy, force of friction times distance. From here, I'm solving for force of friction, so I can just divide by d, and I get mgh divided by d, and now I can plug in my numbers. 6 kilograms times 9.8 meters per second squared times 5 meters, all over 19 meters, gives me a force of friction of 15.47 newtons. That's how much the force of friction has to be. Finally, number 25, a CSI team is going to test the muzzle velocity, or how fast the bullet goes, of a gun that was used in a crime. To do this, they're going to fire a 0.1 kilogram bullet into a block of ballistics material. That picture is available on your review paper. They know that the ballistics material will exert a resistive force of 15,000 newtons on the bullet. If the bullet travels into the material a distance of 0.04 meters, how fast was the bullet moving when it was fired? So let's take a look at the types of energy it has at the beginning of the problem and the end. At the beginning of the problem, the bullet is flying out of a gun. So it's definitely going to have some kinetic energy because it is moving. And that's actually what we're trying to figure out. How fast was it moving? It's going to have no potential energy. I know that it's above the ground, but it's not getting any higher or any lower in this problem. Gravity is not an issue, and there's no springs or bungee cords. At the end of the problem, it doesn't have any potential. It's no longer moving. All of the energy is going to be taken away by that resistive friction force of the ballistics material. So that's going to be thermal energy. Rewriting my equation, kinetic energy is 1/2 times the speed squared. Thermal energy is force of friction times the distance that the bullet went into the block. Solving for velocity, I'm going to multiply by 2 or divide by 1/2, whichever your preference is. In this case, the 1/2 is in the denominator. And I'm going to divide by m as well. That's also in the denominator. Then I take the square root to get rid of the squared. And I get 15,000 newtons times 0.04 meters, all over 1/2 times 0.1 kilogram. Put that under your square root in your calculator, and you get that the bullet is moving with an initial speed of 109.4 meters per second.